Okay. So, welcome to this fifth lecture today on fluid mechanics. And today we will continue to talk about our first boundary layer problem. We started last time about the Stokes' first problem, or the Rayleigh problem. And today we'll continue with that. And towards the end, we will then also go to the Stokes' second problem, which together form kind of two different types of solution procedures, I would say, that you can use for boundary layers. So that's the plan for today. So entirely focusing on these Stokes problems. But before we do that, I would like to summarize what we did last time, as I usually do. So last time we talked about vortices in the beginning. In particular, we talked about one specific vortex, or a vortex model, that is called the Rankine vortex, or it was devised by Rankine some time ago. And the idea with the Rankine vortex is that you define a certain size of the vortex. You're given with the length A, or the radius A. And the idea is that you have inside this radius A, you have a solid body rotation. So you have a rotation or a vortex that is characterized by having a constant vorticity inside, and then the vorticity outside would drop to zero, and you would have zero vorticity outside. And that means at the end of the day that you have a solid body rotation inside, which means that the velocity here in red would increase proportional to the radius first, up to this point at the radius A, from which on the velocity would decrease as a function of 1 over r further out. So you would have this kind of bent decrease. So this is how a Rankine vortex would look like, and how the velocity field actually feels or convects particles. This is something that we looked at last time with a quick video, where you could actually see the convection of random particles in a flow field dominated by such a flow. The advantages of this Rankine vortex model, as opposed to just using kind of an irrotational vortex or a solid body rotation in general, is that first of all, we have a bounded, we have no velocity singularity at r being zero, meaning that the velocity does not go to infinity as it would go if you just had 1 over r, starting from zero. So the velocity is actually bounded in the center, which it should be. And typically, actually, the velocity in a vortex center should be low. Just think of, tornadoes, for instance. Inside the center of the tornado, the velocities are actually low. It is that when you go further outside that you have very strong velocities. At the same time, you also have bounded vorticity, meaning that you can associate a certain value of the vorticity to a vortex. So in this case, for instance, the vorticity would be kind of the area, the area of the circle with a radius of a times the constant vorticity that you have. Now for the Rankine vortex, you can then define its vorticity. So you say inside it has a value of 2 omega. This is just a question of definition that you have the factor of 2 in there, which relates to the the speed of the angular velocity, as we discussed also last time. And then outside, the velocity would be 0. And of course, for the velocity itself, this then translates to this linear and 1 over r dependence inside and outside. Another thing that we discussed last time quite extensively was the discussion we had about the pressure, how the pressure should be inside a vortex. And we realized that the pressure in a vortex center is actually lowest, and then it increases the further out you go. And we realized that the reason for this behavior of the pressure is actually related to the centrifugal or centripetal forces that you get in a vortex. So it has nothing to do with vorticity or Bernoulli or anything. It is actually related to the forces the centrifugal forces that are needed or that arise when you have swirling motion. So that's why you have the lowest pressure in the center and increasing pressure outside. And then we did this derivation to come up with an expression for the pressure in the case of the Rankine vortex. And I guess the expressions are written here. We start here in the center at 0, and we get the delta P as the pressure difference that you get from the surrounding pressure and the pressure in the center. And this pressure difference, in some sense, can be viewed as one way of characterizing the strength of a vortex. And the value here is actually given by rho times omega squared times a squared. So it's dependent on the amplitude, omega squared, and of course the radius, a squared. So this was about vortices. And then we went on to look at also circular pipe flow. Essentially, we looked at another solution where the vorticity equation can be used to calculate axisymmetric unidirectional flow. And pipe flow was one example of those. Pipe flow, also called Hagen-Poiseuille flow, or circular pipe flow. We calculated the exact solution, so the exact velocity profile of pipe flow, and that's essentially what is given here. So we saw that the velocity profile is also very similar to what we calculated earlier when we looked at channel flow. We have a quadratic dependence on the radius, which then gives rise to a parabolic shape. And we have a prefactor to this parabola, which would describe the centerline velocity. And of course, we derived a number of other relations last time. So for instance, the friction, where we saw that was dependent on 64 divided by Reynolds, for instance. We looked at the bulk velocity, where we saw that the centerline velocity is actually a factor of 2 higher than the bulk velocity, which is different from a channel. Yeah. So there were a few things that we discussed. In particular, also we then came up with a kind of a general form of the solution, which we could then use to distinguish between shear-driven and pressure-driven flows. Yeah, and then finally, we started to look at our first boundary layer problem. So just to keep in mind, the boundary layer is the case when you have one solid wall, and then you look at the flow field above this solid wall. And we did that now in the context of the first, or the Stokes first problem, or also called the Rayleigh problem. And the reason why this is Stokes' first problem is it was one of the two problems that he devised at the time, so 200 years ago, where one could find, with the available mathematical tools, one could find an analytical solution quite easily of the Navier-Stokes equations. And we're now following these solutions, and we're using analytical methods, or a specific analytical method that we can solve this problem in an elegant way. So the idea of Stokes' first problem is that you have a flat plate and you have a still fluid around, and then we start to impulsively move or accelerate the lower plate such that it travels with a constant speed of v in one direction. And of course, without loss of generality, we can assume that this v velocity is aligned with the x coordinate of our problem. And the question then is, how does the velocity profile develop in the free stream on top of the plate when we have this impulsively started plate? And of course, what happens is that this higher velocity is slowly diffusing into the domain, and so we can assume that that development is essentially as indicated in this sketch. First, we have a very sharp gradient, and then when we wait longer and longer, this gradient gets smoother and smoother by the action of viscosity, up to the point that maybe at time infinity it would just be a vertical line. So everything has diffused into the domain. But of course, now we need to we want to solve that analytically. So we want to work on a good solution of that. And we started by formulating the Navier-Stokes equations and the continuity equation. And essentially, we have found this solution that is written here, or this equation that is written here. Du dt equals nu times d squared u dy squared. And of course, this is a second order partial differential equation. So now we cannot simplify it into an ordinary differential equation, or rather, we cannot do that yet. So for the time being, it's a differential equation, partial differential equation. So that means we need to specify initial and boundary conditions. Initial conditions, of course, are the velocity is 0 at time 0, and the boundary conditions are that the lower ball moves at a certain speed, v. So this is as far as we came last time. So now we need to start to find solutions to that. So before I start with the new material, I would like to ask whether there is any question or anything that we would like to discuss more on the material from previous time. Okay, but then let's just start with the new material. So the idea now, or the problem that we need to discuss is we need to find now a solution. So we need to solve this problem for the velocity u as a function of y and t. So two variables that we need to, or the solution is dependent on y and in t. But how do we do that? Well, the idea here is that if we just look at the expected solution, we can somehow think that there is a certain similarity between all these different solutions that we have. So just imagine if we now stretch the y-axis for each new time, so that essentially this one, so for instance, this solution would kind of be elongated in the y direction up to the point that it would may fall on this other solution, which is at a later time, and so on. So the idea would be that there may be a scaling that would be possible to combine the two variables y and t into just one variable. And of course, as soon as we have a differential equation that is only a function of one variable, we actually have achieved to go from a partial differential equation into an ordinary differential equation. So the idea how to solve this problem is, I'll just write it down. So the idea now would be is to combine the two independent variables y and t, to combine y and t into a single variable, and this is called a similarity variable. And with this similarity variable, we could then stretch the time or the space in such a way that they all collapse onto each other. So we would like to combine those into a similarity variable, and typically we use actually the Greek letter of eta for a similarity variable. So that's just a convention. So that means we would like to write this u, which was a function of y and t, to actually be a function f of eta instead. And this eta necessarily needs to be non-dimensional, because it cannot have a dimension of a time, it cannot have a dimension of a length. It needs to be somehow non-dimensional, such that we can actually do this stretching. So what we want to find is a similarity transform from y and t into eta, such that eta is non-dimensional. That already gives us a hint of how we could actually do that, in what way that in what way we could actually find this similarity transform. Well, let's look at this. So what do we have really? We have our time variable t, and this is, of course, has a unit of a time here written in with a capital T as a time unit. Then we have the spatial variable y, and of course this is of a unit of a length here written with a capital L. What else do we have? Well, if you now look at our differential equation, we have now used t, we have used y. Of course, we have the solution u, but that's the one that needs to be scaled. But of course, there's something else that we have. It's this guy here. That's the viscosity. This is a parameter that goes in, and obviously, the viscosity has certainly an effect on how this scaling would look like. So if you now just look what the unit of this eta is, that is a unit of length divided by time. Okay, now what we want to do, as we said before, we would like to find this eta in such a way that it's non-dimensional. Now we have these three parameters or units, t, y, and nu, and we would like to put them together in a non-dimensional way. Actually, there's only one way of how this can be done, namely by combining t and y with nu in the way as follows, that eta actually becomes y divided by the square root of nu times t. So this is the only way of actually making a non-dimensional eta based on t and y and eta. So that's the way that we can make it non-dimensional. So what's now the consequence of that when we now try to understand the solution of our problem? Well, it would essentially mean that if we are able to write our solution, so our velocity profile, as a function of eta instead, it would then mean that for a fixed eta, it would actually mean that if my time goes up, so if I increase my time, so I go to a later time, that would essentially mean the same as that my vertical distance goes up because I divide y by the square root of t. So that means essentially at a double height, that would mean that this would correspond to a time that is 4 times later. So the t would be 4 times later. So wait, let's say 4 times longer, if you wish. And of course, that's exactly what would happen here. For a fixed eta, so for a fixed value of my solution, perhaps, it would mean that if I increase the y by a factor of 2, it would correspond to a time that is 4 times later. Okay. Now we have introduced this in this way, but now we still need to solve something with it. We still need to introduce this eta somehow in our equations. And I guess if we do that now mathematically, then it will also be clear how to incorporate this in our as a way of solving or reducing partial differential equations into ordinary differential equations. If you now do that mathematically, it would be in the following way, that essentially we try to replace all these derivatives with respect to t and with respect to eta, with respect to y, with derivatives with respect to eta. So just to illustrate to you how this works, so if we have the first term, du dt, and if we now just replace the u with with an f of eta instead. So we have d dt of f of eta. And now we can just use all the rules that we know from doing derivatives. So it's essentially the chain rule that we need to use here. So that would now be df d eta times d eta dt. That's just the chain rule applied. Keep in mind that here I'm using ordinary derivatives because f is only a function of eta. So therefore I can change there from partial derivatives to ordinary derivatives. Well, of course, in going now from the Leibniz formulation of derivatives to the formulation with a prime here, I can write that this is f prime times d eta dt. Okay, so this was the udt. Now we can kind of try to go forward a little bit or continue with this, because now we have this derivative, d eta dt. Of course, this is something that we actually know how to express because we have here a definition of eta. So d eta dt. Well, what is d eta dt? That would be d dt of the definition y divided by the square root of nu t. And this is if I'm now taking out everything that is constant, so y divided by the square root of nu times d dt of well, t to the power of -1/2. And if I do that, if I calculate that, it would be -1/2 of y divided by nu square root times t to the -3/2. And this gives me then -1/2 of y divided by the square root of nu t times 1 divided by t. Of course, the reason why I took this out is because this is, of course, eta. So that means that this becomes -1/2 of eta divided by t. Actually, I should maybe write it like this. Eta divided by t. So that's, of course, a very nice result, because now I see that this derivative that we have up here, so for this term, we actually found that we can actually replace that with -1 times eta divided by t. Okay, let's just continue with doing also the second derivatives, and then we can put everything together, and then we will directly see why this is actually an interesting way of solving. So the other derivatives that we need to solve is actually du dy, and in particular d squared u dy squared. But we start with the first derivative first. So we have df d eta times d eta dy. Of course, this also becomes f prime times 1 divided by nu t. So d eta divided by dy. And of course, now we can continue d squared u dy squared. That would just be d dy of exactly what we have just calculated, d dy of f prime of 1 divided by square root of nu t. Now, of course, this all becomes a little bit annoying with all these derivatives, but in the end, it's nothing very strange. It just becomes, now with the product rule, it's df prime d eta times d eta dy times 1 divided by nu t, chain rule, of course. Yeah, now also here I can of course see that this becomes f double prime, the first term here, and then we have this d eta dy times 1 over square root of nu t. This just becomes 1 over nu t. So this would now be the second derivative. Okay. Well, now I put everything. Now I put everything into my governing equations. We combine everything. So we started with the equation that we had from the beginning. So that was du dt is nu times d squared u dy squared. So this was the equation. But now we fill in essentially for du dy. We fill in what we have obtained here, or of course this one is replaced with this one, and for d squared u dy squared, we fill in this term. Okay, now if we do that, well, what do we get? We get minus 1/2 nu divided by t times f prime. That's for the first term, and that is then minus nu times, not minus, I mean nu times f double prime times 1 divided by nu t. Okay, now we can work a little bit on that. Well, we see that the nu falls out. We can also see that the t falls out. And what we're left with at the end is an equation that looks like this: f double prime plus 1/2 times eta times f prime equaling 0. So that's the result that we get. Now, this is actually a very interesting result. And because this is now an ODE, so it's not a PDE anymore, it's an ODE, and it is written entirely in f of eta. And as prefactors of this f, there is only eta left. There is no nu, there is no t or no y left. And of course, you can now think that this is magic, that all of these disappeared. It's actually not magic. It comes from the choice of how this eta was actually defined. And the definition of eta was such that we required that this was a non-dimensional, non-dimensional. So the fact that we could actually find such a similarity transform in a way that everything else disappeared, so the t's and the nu's and the y's disappeared, that we could write it in this way, shows us that we can actually now solve this ODE. Then once we have a solution f of eta, we can then go back using the definition of what eta was to calculate our u as a function of y and t. So that's the beauty of this, that we have an ODE entirely in eta. There is no nu, there is no t, and there is no y left. These three parameters, they just go in the definition of eta. So that's the thing. Okay, but once you believe that this is a good way of solving it, or rewriting the original problem, we're still in the situation that we haven't solved it yet. We still have an ODE. Of course, it's much easier now because we went from the PDE to an ODE, but of course we still need to solve it. That means that's the next step. So let's solve this. Let's solve this ODE in an appropriate way. Well, of course, it's slightly annoying because it's not constant coefficients here, because we have the eta, one eta, which is outside, so that's slightly annoying. But there is actually one way of solving that quite in a straightforward way. Let's just rewrite it in a way that is a little bit easier. Namely, we just put everything, the f's on one side and the etas on the other side, which will look like this. So f double prime divided by f prime is -1/2 of eta. So there's just rewriting the original equation. And now the point would be, now we can integrate both sides independently. So we do an integral with respect to eta of the left side, and of course also on the right side of -1/2 of eta d eta. And we do that between 0 and eta to avoid integration constants. Now you see why this is nice, because if we do that on the left side, we actually get as a result an ln of f prime evaluated between 0 and eta. And if I do the integral on the right side, I actually get -1/4 eta squared evaluated between 0 and eta. Now, if I'm evaluating these integrals, I get ln of f prime divided by f prime of 0, and on the left side I get just -1/4 eta squared. So now I would like to continue extracting f here. I can get rid of this ln by just taking or doing an exponential of this. So if I do that, I get f prime of eta, which then would be f prime of 0 times e to the minus eta squared divided by 4. I can now call this to be b if I want, just if I want to have want to introduce a simpler letter, because this is just a constant. It's f prime of 0, so that's just a constant value. So I still have an f prime, so I can do one more integral. So I can go from f prime, I can go to f by just integrating this once, and this would be an integration constant a plus the integral from 0 to eta of b times e to the minus eta squared 4 d eta. And now at this point, I would need to calculate somehow a and b. Well, how would I calculate a and b? Well, in this case, these are of course related to boundary conditions. So we need to somehow include also the boundary conditions that we have from the beginning. Now, the thing is, we of course need to formulate these boundary conditions also in terms of the similarity variable eta. Well, I guess we would like to have a boundary condition at when eta is going to 0, and a boundary condition of f when eta goes to infinity. So close to the low values and high values. Well, if we now look at how eta is defined, so eta is going to be 0 if y is going to be 0, and eta is going to be infinity. Well, eta is going to be this we see afterwards. What was happening with eta is going to be to go to infinity, but it would essentially mean that either y is going in infinity or t is going to be 0. So let's go down. So for the first value, when eta is going to 0 towards 0, well, that means that f needs to take the value of the velocity at the wall. Of course, in our case, this is exactly the v velocity that we have at the wall. And for our functional form here, f going to be 0, that means that the integral here would be 0, and that means that the value of a would, so the integration constant a would be v. Now, the second point here, when eta is going to be going to infinity, as I said before, this is either this would happen either when y is going to infinity, so far away, or if the time is going to 0. Well, we can think of both of them. If y is going to infinity, so far, far away, of course, that means that we're so far away from the wall that we're still having the initial condition being present there. So that would mean that the velocity there would actually be 0. Or we can also think of any y position at time 0. But of course, that's also when we still have the initial condition of f being 0. So that means f at infinity is 0, and infinity, when we now put this in the equation, means v plus b, the integral from 0 to infinity of e to the minus eta squared divided by 4 e eta. So this would now define the b. Okay, so now we have an equation for f with well, one expression for a and one expression for the integration constant b. So in principle, we have now our solution of f. We can evaluate a and b, and we can put that in, and then we have our solution. There is actually just one more step that we can do, which is not necessarily needed, but it gives us a nicer solution. There is actually a nice mathematical formula, namely the integral from 0 to infinity of e to the minus ax squared dx. This can be calculated, or this can be evaluated as 1/2 of the square root of pi divided by a. So this is a mathematical identity, and of course this is heavily used when you look at a Gaussian distribution. It may be slightly surprising why this exponential here, the integral of an exponential, suddenly gives rise to the square root of pi, but this is just the case. Now, if we use this, and we use this in particular to calculate b, we can evaluate this. I'm inviting you to do that at home if you wish. The result will be that this b evaluates as minus v divided by the square root of pi. And of course, it's clear that the square root of pi comes from this one here, and of course the v comes from the here. So with this final identity, we can write down that we have the final result for f at least. F of eta now becomes v times 1 minus 1 over the square root of pi times the integral from 0 to eta of e to the minus eta squared divided by 4 d eta. And this here is now our, what we would call the similarity solution for Stokes' first problem. This is the similarity solution. I'm calling this the similarity solution because it's still written in terms of the similarity variable f of eta. So it's written in the shape or as a function of eta, which was our similarity or our non-dimensional similarity variable that we have introduced here in the beginning. So there is no y and t yet, but of course we know y and t because we have this definition of how to evaluate eta as a function of y and t. So this here is our similarity solution. Now, of course, now we could stop at this point. There is actually yet another step that we can make, just to write it in a kind of a shorter form, or maybe in a form that is easier to remember, because there's yet another mathematical definition that we can use here. Namely, we can rewrite this as an error function. So keep in mind, or remember, that there is something that is called an error function. The error function as a function of the variable z is defined as 2 divided by square root of pi, the integral from 0 to z of e to the minus q squared dq. So again, this is just a definition. This is a function that is implemented in various computer programs or calculators. And of course, it has its origin in Gaussian distributions. Now, what we can do is we can realize that actually the error function is kind of similar. We have here something that is somewhat squared. We have an integral from 0 to z. Then we have this pi here. So I mean, there's certainly a similarity between our similarity solution and the error function. Now, what we can do is, by just using a substitution, so we substitute q to be eta divided by 2, which then of course becomes that q squared would be eta squared divided by 4, and the d eta in that case becomes 2 times d q. And if you put all of this together, we actually get f of eta then becomes v times 1 minus 2 pi divided 2 divided by the square root of pi, the integral from 0 to eta divided by 2 e to the minus q squared dq. And now, taking in the definition of the error function, we will see that this becomes actually v times 1 minus the error function of eta divided by 2. So this is the f of eta. And now, since we know that f, when we go to where we started, where did you write that? Up here, we said that u of y and t is f of eta. That was kind of the definition that we had here. We can now go back here and write, and that's now really the final result that I will write down. U divided by v, which is the non-dimensional velocity, is 1 minus the error function of, well, nu divided by 2, or eta divided by 2, and eta divided by 2, of course, is y divided by 2 times the square root of nu times t. So this here is now not our similarity solution anymore. This is our real solution in terms of u, y, nu, and t. So we have now found a solution of the diffusion equation, the unsteady diffusion equation that we had here in the beginning, using the similarity approach. When we combined the dependence on y and on t into one variable, and then we could find this solution here. Of course, now I can, and that's maybe the last thing that I would do before the break. I can, of course, draw this just to give you also a kind of a visual impression of how the solution looks like. I would actually like to draw it in two ways. First, I would like to draw it in terms of the similarity variable. I would draw here u divided by v, and obviously I would start here at 1. That's at the wall. Then I have here my similarity variable, and the solution that would be kind of this equation here would look something like this. This is my similarity solution, or similarity profile if I want. The second graph, I can actually show, or I can plot u divided by v, but now as a function of y. And of course, as soon as I draw it as a function of y, I need to draw a different one, a different line for each t, because now we're actually having the solution as a function of y and t. And of course, that's exactly what we already drew earlier. If this is again the value of 1, where it starts, and maybe initially it looks like this, and then later it looks like this, and then like this, up to the kind of the point like this. Again, this is then my time dependence. My time would increase kind of from a more full profile to one that is kind of more more constant or more vertical. Okay. So with this, I would like to now take a break of 15 minutes, and we continue at 4:15.